Okay, welcome back to the 424 School of Engineering. This is the last module of this series. Today we're talking about chassis and powertrain, specifically electric powertrain. And I am very excited about electric powertrain, and I hope I can explain to you why today and the benefits of it. And before I start talking about this, I just want to show you some developments on pairing.com very quickly. So last week I talked about the bigger plan, the token, the innovation network that we are developing. How our aim really is to, allow everyone very easily to take ownership of the network. And this is work in progress. And every week we are developing this platform that you see here. You're all familiar with pairing.com. This is, as a reminder, this is a dashboard, a public dashboard where you can see live all our developer, the core team of Pairing, effectively communicating every day through these messages and threads. So it's a bit like WhatsApp, but for our team. It also has the events that you can attend. So obviously, right now we're in the 424 school. Next week we have our core team meeting, like we have nearly every week. And then we are doing continuous fundraising through the token sale. And as you can see, we've added some of the branding for the token here. And just as a development as well, the platform is getting more and more integrated around this the PRN token. When you go on this buy PRN page now, you can basically see a price for the token, which is, this is set for me as pounds, but you can have it as euros or US dollars. And the price basically evolves every day at a rate of 10% a year at the moment. I want to stress that there's going to be a lot of changes happening in the next few weeks on the user interface to make it more and more clear what we're doing and how it works. But you can already start, purchasing some tokens today. And one thing you have to remember is the price of the token will never be as low as it is today, because the price just keeps increasing over time. The rate of increase of 10% a year is dictated by us and how we see the network growing. But when 424 project gets effectively physical and gets started soon, the rate of increase will go up. We'll go from 10% to something like 25%, which is a really interesting growth rate. This is what tech companies typically grow at. And it means that over a 10-year period, the value of the token will be multiplied by 10. So that's what a 25% rate increase per year means. What we're going to add very soon is some graphics on pairing.com showing, explaining the trajectory of the token price and where we're going. And that will also explain a little bit about our strategy. Okay, thank you. I was muted. So my internet connection dropped. I'm back on now. So sorry about that. So I don't know where I left it. Let me share this again. Okay. So as I was explaining, basically, this page is where so we've made changes on the pairing app, integrating the pairing token. This is where you can acquire the token, and the token has got a price um, here in US dollars, and I'm just going to refresh because it should be in pounds for me. That's it. So over the next few weeks, there's going to be more developments. We're going to add graphs to this page explaining the trajectory we're on and the milestones we thought for project and how we're going to grow the token, the network, and the plans for the future. And as you already know, you can access the list of token holders here, all on pairing.com, and how many PRN tokens everyone holds, and the value for the price that we are giving to the token right now. Okay. So just remember this: that the price of the token will never be as low as it is today because it just keeps increasing automatically in the app. And the big picture and the aim is really to create this fully managed platform where everybody can just come very easily and acquire part ownership of the network and be on the journey of growth with us. Okay. So this is quite innovative, and this is effectively the tokenization of the network is something that follows new developments in the financial world, and more companies and organizations are going to do this. So we are at the forefront of this, and I'm really excited about developing the team this way. And I really believe that by people investing in pairing, that emotional connection by being invested will really create, very, very strong core and a very strong team that more and more people will want to join eventually. Okay. Any question on the token and the platform? Okay. All right. So I'm going to jump over to, okay, Lauren, you've got a question.
Yes, thank you. I think you mentioned an app. Is there an actual app, or are you referring to the website that you have?
It's the website. It's the
The
pairing.com
website.
website,
Okay.
which you can, by the way, install as an app on your phone as well. I have it as an app on my phone.
Mm.
It's not on the App Store, but you can install the website as an app, and it works like an app.
Can you share into our group how I would do that? Unless
Yeah,
it's really easy to explain here.
it's no different to installing any website. You can put it as an app on your home
Hmm.
screen on your phone.
Yeah.
So I've got an iPhone, but you can do it on an Android phone, I believe. So I think when you're on our website, you have to basically go and select Add to Home Screen, something like this, and it will
Okay.
basically put the pairing logo as an icon, and that becomes like an app that you can always jump back in.
Yeah.
So that's what I do on my side, and a lot of people do.
That's actually really cool. I've never heard of an opportunity to be able to do that. So it's
Yeah,
quite new to me.
yeah, yeah. So the website has been developed so that it works like this. And I didn't want to have an app on the App Store. Just
Mm.
the great thing about the website compared to an app is that it's automatically updating all the time. So
Yeah.
when you've got an app, you need to go back and update it when you're asked to update it. Or
Mm.
it can be manual sometimes, and you're not always on the last version. Where with a website, the way it's been built, every time you go back on it, it will go to the server and ask, to refresh the pages to the latest version. So you don't need to worry about it.
Yeah. That's brilliant. That's really good.
Okay.
Thank you so much for explaining.
Yeah, no problem. You're welcome. Okay, so let me jump onto the topic of the day. So today we're talking about chassis and powertrain. and I will explain. So it's two sections today. I'm gonna start with the chassis. There's not a lot to cover, to be honest, but I will explain the way, the strategy behind the design of 424 chassis, and what we've been doing so far. So obviously, 424 uses primarily carbon composites material, especially for, and actually on this picture you can see the chassis extends to the back because the battery is inside the monocoque, and we're going to open the card in a minute so you can see it. So in traditionally with an engine, the engine is part of the structure of the car, is bolted at the back of the chassis. So you can say that actually there's quite a lot of metal on traditional, even Formula One cars. The structure of the chassis of the car, there's the engine in the middle and the gearbox, and this is like a lot of metal. But on an electric car like 424, we're replacing a lot of metal with carbon because there's no engine anymore. The battery effectively is not structural, it's inside the chassis. The chassis is carbon. And then at the back of that, there is another carbon structure that houses the electrical motors, and I'll show you that in a minute. These images actually are historical images from the LMP1 work we did when the car was going to be an LMP1, traditional LMP1 car. And just showing you that at the time, and this is like 10 years ago now, we were still designing in NX, and we were doing stress analysis. I had somebody that for nearly a year did
Nico,
stress
excuse me,
analysis.
but you are not sharing a screen now.
Okay. Thank you for that. It's the last module of the series, but I should be used to this now. But obviously, it didn't go as well today. Okay, so I'll start again. But so chassis and powertrain. Okay. So what I was showing here is so carbon composites is what we're using primarily for the car. These images here of the chassis. This is a side section, and this is taken from the LMP1 car. Because that doesn't have the housing for the battery at the back. So what we did 10 years ago is we had, so I had somebody doing stress analysis for a year, and it was done in Nastran at the time. So sort of like traditional old school, I would say, tools, and we did a lot of analysis. If you look at the load cases that we have to design for, we're going to open that document here. So this document summarizes the main load cases we are designing the structure for. And the chassis is mainly designed for safety loads. So these are specifically static loads. You can see it's in kilonewton here. So there's a list. It ranges from 30 kilonewton to 300 kilonewton for the biggest loads. And these loads are the loads that basically are applied on the chassis. Like this is one example for the front rollover structure. Okay, these loads are coming from the technical regulation, safety regulation. So we are complying to this 4424. We have the suspension loads. So these loads are coming from the different suspension legs, and that will also push on the chassis. Okay, so remember when we talked about suspension, we have an idea for every single load on suspension links, and we are using these loads to design the chassis mounting points for the suspension. So you see the loads are variable, the maximum 197.5 for the rear push rods. Actually 105 kilonewton is the maximum here for the rear suspension lower rear leg. We've got also some aerodynamic loads. This is coming from CFD. So we know how much vertical load is created from downforce from the front splitter, which is like the front wing, I like to call it the front wing now, actually. So I'm going to change that. And this is 26 kilonewton in this case. That's going through the 4 pillars. The rear wing is producing 15 kilonewton and the floor 30 kilonewton. We are putting a safety factor here. So the actual load measured is this one, then we multiply by 1.3, and the test load will be higher, just to give us a bit of margin. On the suspension, we're having a safety factor of 1.5. We also have a target for the torsional stiffness of the chassis of the whole car. So we are applying torsion from the front suspension to the rear suspension, and we're trying to keep the stiffness to a certain level for vehicle dynamics purposes. And then we have what we call nonlinear crash loads. So these are the impact loads, one at the front, one at the back, one in the steering wheel column. So effectively, we took the time 10 years ago to design the LMP1 car with all these loads taken into account. When we went to 424 electric version, we haven't yet updated these loads. So excuse me. What we did is we we took the design from the LMP1 as our reference for dimensioning the, for example, the rollover structure and the reinforcement, and that's become the baseline for 424. When we go to detailed design and manufacturing of 424, we're going to redo a lot of stress analysis. So I'm not doing this right now because typically it's not a good investment of our time to do this now. It's better to keep evolving the performance of the car through aerodynamics and suspension and vehicle dynamics. When we have the budget to build 424, we're going to work closely with the manufacturer of the composite chassis and the rest of the car. And we're going to redo all the testing in stress analysis to refine the final thickness of the panels and everything. And we'll do it with the people who are going to build the car, okay? One thing I've put here is our composite specification document. So it's just a summary of the type of material that we use. This is for, again, carbon composites. So in this table here, you've got various type of fibers that we typically use. And then matrix is the resin that we use. And then the prepreg is the combination of the fiber and matrix. Okay. And then you're gonna have a core in between, in the middle of your skins, the outer and the inner skin. So we use honeycomb or foam typically. But what I want to show you here is, if you take the fibers on their own, and you look at the tensile strength of a fiber, is extremely high. So the fiber on its own is an extremely stiff and strong material. Here we've got, you know, numbers like 4,000 up to 6,000 megapascals of strength. The matrix or the resin, in comparison, is very low strength. You could imagine you could a small piece of resin, you could break it with your own hand. So the strength is more like 80 or 65 megapascal. When you combine the resin and the fibers, depending on the proportion of resin and fiber, you get something that's in between the fiber strength and the resin strength. But you need both to make a panel, obviously, because the fiber on its own wouldn't hold, and the resin is not strong enough on its own. So I quite like to look at these numbers just to understand what a panel of carbon composites is made of and why you achieve these sort of strength numbers. Interestingly, a strength of 800 megapascal is quite similar to aluminium. I'm saying this because when you want to do stress analysis in a quicker way, and I've done this loads in my career and for 424, you can use aluminium actually as a material to replace composites if you want to have first order simulation and approximation. The other number that's very similar is the modulus. So this is effectively like how strong the spring is, the relationship between elongation and force. And that sort of tensile modulus is quite similar to aluminium as well. In fact, it's very, very close. And this is the number that matters for stress analysis. This is what's going to dictate the deformations. The strength, actually, aluminium is closer to 450. So if you're using a high, what we call a high strength panel, like this one, you're going to be higher than aluminium in this case. What we're looking at really is actually for stress analysis, we are looking at deformation and level of stress, but we're staying in a linear region, so we don't have failure in this case when you do linear stress analysis. So using aluminium is really good instead of carbon panels when you don't have the software that can simulate carbon panels. So it's a good way to do simulation. The other number that matters when you do stress analysis is the Poisson ratio. So it's more or less, if you pull on your material, is how much deformation you're going to get in the other direction. And that, again, the 0.38 is very close to aluminium. The big difference between composites and metal is the density. The density of a carbon panel is 1.5. So it's 1.5 times the mass of water. If you compare that with aluminium, aluminium is 2.7. So now you're seeing a material that's significantly lighter than aluminium, but has got the same or higher strength and the same stiffness. So that's why composite is so good. If you take another material we use is a steel, but still the density is more like 7.8. So it's much heavier than aluminium and carbon. And it will have a higher strength, but when you calculate it against the mass, it's not a good it's not as good as aluminium and not as good as composites. So composite is the best, what we call specific strength. So the strength in ratio to your mass. A last material that we use quite a lot is titanium, and titanium actually is is better than steel. It's more or less the same strength and stiffness as steel, but it's lighter. And it's got a better overall strength than aluminium as well, compared to the mass. But it's not as good as carbon. So in order of material, the best is composites, carbon composites. Second would be titanium, then aluminium and steel. But some parts, so then you would say we can build everything with carbon. But some small parts cannot be built easily in carbon. So that's when we have to use steel or aluminium. So depending on the size of the parts, you're going to choose a different material. So all the big parts will be composites on the car. So let's go into the CAD quickly to illustrate what I've just explained. So as I said, just loading this. So internet's a bit slower tonight. In fact, just a second. Just gonna go by on the higher speed internet now. I'm not having much luck tonight. So it should be fast enough now. Okay. So typically what, again, it's a bit more time to load. But what I wanted to say again is when it comes to defining which material you're going to use, what I've learned from my career is, from my experiences, the big parts definitely go with composites because they're easier to manufacture because they're bigger with the molds and the process of manufacturing. But when you go to smaller parts, and I'm thinking of a gearbox, for example, I see a lot of projects where in Formula One, for example, or other projects, the gearbox sometimes is made of composite, sometimes is made of aluminum. And there is this the difficulty, in theory, a carbon gearbox would be lighter, but when you look at the manufacturing process, the part is too small and too intricate in terms of shape to make it easy enough to manufacture, and then you're losing the mass advantage. You're starting to add more mass because you're adding more inserts into the part. And actually, an aluminum gearbox is still the best solution. Okay, so I hope you're following what I'm trying to explain here. So I just wanted to show you that when you look at the car. Okay, let's skip this view here. So we take the chassis and we're going to isolate this. And I want to add, so I want to show you what we call the spline for the car that holds the loads. So it goes from, I'm going to go back with the chassis again. Okay. So what I'm showing here is effectively all the loads are held by this structure. And everything you're seeing here highlighted is made of carbon again. So in the past, this block here would be the engine, so it would be aluminum. This block here would be the gearbox. Because in the past, you had 7 or 8 gears in Formula One cars, so that's a lot of metal. But with 4x4, we're going to something that's much more carbon composites. So that's point number one. And that structure needs to hold everything else. So the floor needs to bolt to the bottom of the chassis, and ideally the floor doesn't need anything else to hold itself. So everything bolts on the spline, and ideally it holds by itself. It's not true for all the panels. If I think of, for example, if you take this panel, obviously, that will have to be held by the floor, but the floor itself needs to be thick enough. So the floor is an interesting one because aerodynamically, you want the thickness to be as thin as possible. And I've seen in Formula One floors that are getting thinner and thinner, but the floor actually needs to make sure it's stiff enough in bending. So as I said before, the floor is bolted to the chassis in the middle, and the outside needs to hold the loads of some other parts and just the aerodynamic loads. Okay, so here I've selected a thickness of 10 millimeters. It's quite thin, but it's thick enough so that typically in the 10 millimeters, you're gonna have two skins of carbon and a core in the middle, and the skins are going to be 2.5 millimeter each. So you're going to have 2.5 millimeters of carbon, 5 millimeters of honeycomb or foam, and another 2.5 millimeters of carbon. Okay, and that's going to create a fairly stiff assembly. In fact, this is quite heavy. Maybe we're going to go lower than this. Maybe 2 millimeter of carbon each side and 6 millimeter of core. That's typically a construction for a part like this. The chassis itself, the way it's designed at the moment is it's missing some details. So if I do a section, here you can see we have some big beams for the rollover structure at the front and at the back. And also there is a connecting beam between the two. But the rest is fairly empty. And we are missing some structures that will need to be added. For example, where the suspension mounts, at the moment we only have the thickness of the skin. So we are missing some structures that, as I explained before, we're gonna refine when we get to manufacture the chassis. Okay. So this model is still missing some details when it comes to structure. So right now we only have a skin of carbon, and if I measure the thickness of it, that's only 2.5 millimeter. So obviously that's not enough to hold the suspension loads. So it will end up being 2.5, a core, and another 1 millimeter on the other side, for example, and it will have some beams as well in different locations. Okay. Any question? Another thing I can mention before we go to questions. Some parts we call structural, some parts we call bodywork. So typically a panel like the side pod here, that doesn't hold any significant load. So that's going to be very, very thin, 1.5 millimeter of carbon, maybe just 1 millimeter of carbon and a small core. So that's a body panel. But the pillars, for example, obviously they're holding the rear wing. So these need to be structural, and then you come back to 2.5 millimeter of carbon or 3 millimeter of carbon. The wings also, we need careful attention when it comes to structure. They already have obviously a certain thickness. We wouldn't want to make them thinner because it would be harder to get the structural stiffness that we need. So when I do the aerodynamics, I take into account knowing that we need certain thicknesses in places because there is loads to be held. So as an aerodynamicist, you don't want to just design wings that are so thin that they will not be able to hold the loads. And then at the front, it's fairly simple. You have these pillars here that take all the loads from the front wing. Okay. And that goes into the crash box, which is like the end of the spline, the front end of the spline. Actually, I should say the spine. Spline is something else. So the spine of the car is that center structure I talked about. Okay. Any question on the chassis and structures? Yes, Wojciech. Hi.
Hi. How this spine structure, load holding structure will change in the hydrogen version? Where will the fuel cell go and tanks?
Yeah, no, good question. Thank you. It will look very similar, actually. Let's go back to the spine. So in the hydrogen version, and I don't have all the details just yet, but what I'm anticipating is we're going to still have this volume at the back, and this is where the hydrogen tanks will be. If you look at some of the projects that you see on the internet, the hydrogen tanks are on the side of the car, but that's not going to be allowed anymore in the future. So we're going to have probably 2 tanks of hydrogen behind the driver. We're still going to have a battery, but the battery is going to be smaller, and it's going to potentially sit on the side of on the passenger side, or maybe in that area as well. And then after that, we're going to have the fuel cell stack. And the fuel cell stack is more or less the size of a small engine. And it could fit in that volume here at the back. Whether it can take loads or not, I'm not sure. So what might happen is this carbon structure might need to get a little bit bigger so we can put the fuel cell inside it. And after that, this will remain the same. So this casing, what I call the rear casing, will still have the transmission and the electric motor, the same as now. Okay.
Are the cooling requirements for the fuel cell similar to the battery one?
It will be similar, yes. So you're still gonna have these big radiators on the sides. And to be fair, the ones we have on this car at the moment are as big as it can get. It would be difficult to fit bigger radiators. If we need to fit more radiators, you'll start looking at putting another one on top here, and then you're going to have a bigger bodywork engine cover. Okay.
Mm-hmm. Thank you. What is the honeycomb made of?
Say again, sorry.
What is the honeycomb made of?
It's like paper, really. It's like it's like cardboard paper. It feels like this. It's that sort of structure.
So its primary function is just to make a distance between two skins.
That's right. Yeah, just to create some distance between the skins, so you get more bending stiffness. There's a question on the chat. Will the floor have a wooden plank? So that's a good question. So for the Nürburgring, I've removed the plank. We don't need the plank because the plank is for the regulation, is to control the height of the car. And it's a fairly heavy part as well. It weighs about 4 or 5 kilos. So for the Nürburgring, I've decided we remove the plank to be as lightweight as possible. Wesley?
Have you considered using the bodywork to support the floors to increase the bending stiffness?
So I looked maybe into it, but it's something that yeah, that's a good question, because I did initially look at something where let me show you. My conclusion is no, actually, but that it's not going to work. But if you look at a section of the car like this, maybe like that, the bodywork here goes around. It would be very difficult to support the floor with a shape like this. And also, actually, the engine cover is very, very light and doesn't have much structure. It's not connected at this point.
Looks like the yellow panels, they have lots of vertical sections. They're like a vertical docks. Maybe They can be very stiff vertically.
So you're talking about the rad duct.
Yeah, yeah.
Let me have a move that a bit. Yeah, so yeah, the rad ducts at the moment, they're attached to the side of the chassis. We can't see it here. There's a missing part. There's basically a bracket, carbon bracket between the duct and the chassis. First of all, we need to be able to take the floor off. Yeah, the duct needs to hold themselves. They're not supported by the floor. The ducts are supported on the side of the chassis. So we can take the floor off, we can take the bodywork off, and the radiators are still on the car. And at the moment, there is no connection between the duct and the floor. There will be maybe just a little connection just so that the duct will not move too much. It would be quite difficult to actually pull on the duct as a structural part. You'd have to make it fairly heavy because also it's an open section here.
Yeah.
So again, I'm looking at what I've seen as well in F1, and I'm following. You have to look and understand why people have. So basically, the bodywork is as light as possible. It doesn't support any loads. So really, the strategy is, yeah, the floor needs to hold itself, bolted in the middle, and the bodywork are the lightest panels you can build. And when you attach them together, it's a bit like sewing panels together. They're sort of gaining a bit of rigidity because they're close together. If you take one panel on its own, it's fairly soft. But when you bolt them on together, they're sort of holding nicely together. But they're not able to support the floor, no.
Understood. Thank you.
Okay. Okay. Any other question on this? Okay. Let's move on to the powertrain. So, and powertrain really is actually really important for this car. As I explained, I discovered the electric powertrain when I worked on the Neo car. So this one, the Neo EP9, that was in 2016, and we broke the electric record at the Nürburgring with this car. And it was a heavy car. It was early days, but I realized the potential of electric powertrain is very, very big, and it's definitely gonna. I know it's controversial because a lot of people still love, engine noise and gearbox and shifts and things like this. But there is, in terms of engineering, and it's such an elegant solution. It's a more simple solution. There are some. I think we look back at the engines and the complexity of, the cams and the timing belts and the fact that you need the alternator on it, the vibration because an engine is vibrating. There's a lot of oscillations. You're taking all of this away, and the gearbox with eight gear shifts. You take all of these small complexities and components away, and you have this beautiful single-speed electric motor that doesn't vibrate at all. Vibration is a big problem in traditional engines, by the way. When I worked at Le Mans, we had problems breaking suspension parts, chassis, because the V8 engine used to vibrate a lot. So suddenly you got these rotating machines that are very smooth. And I want to show you this graph, actually. That, for me, is one of the big reasons why the electric powertrain is definitely the right way to go. And it's a matter of time before it becomes the norm on every single motorsport application. Traditionally, so this is a graph of vehicle speeds and torque at the wheel, okay? And traditionally, at low speeds, obviously you need to be in first gear, if you don't have that first gear, the second gear doesn't produce enough torque at the wheel. You cannot pull away, or you have to slip your clutch. The clutch is another component that's, if you think of the clutch, it's completely disappearing for an electric car. There's no more clutch, and the clutch is not a very elegant solution in my opinion, because it's creating heat, and it's a sliding component trying to convert torque in a weird way. And the reason we need clutch is very much because the petrol engines don't have the low speed torque. You can see the gaps here. The second gear doesn't have the torque here, so you'd have to slip your clutch so much to produce that level of torque so you can pull away. So that's why you need the first gear, but with the first gear you still need a clutch, because obviously there is zero torque available at zero speeds, at 0 RPM. Okay? But what you're seeing as well is, as you go through the gears, you're basically trying to produce a constant power curve. So try and remember this curve here. So this is the electric version. That curve here is the constant power. As speed increases, torque decreases. Torque times speed is power. And in fact, this curve is the resulting power. So the constant power here is that decreasing torque in that way. This is exactly what the old-fashioned ICE, so when ICE engines, cars, are trying to replicate. But it's not perfect, because you can see there's some gaps. There are some areas at a certain speed where you don't have enough torque to get to the power level, to that constant power curve I'm talking about. So that's why in Formula One they've added more gears. So you've got 8 gears in Formula One, and this way you're filling some of the gaps. You're making that transition smoother and smoother, and closer to the ideal constant power. But the electric engine is able to produce that constant power curve, and also it's got that torque at 0 speed, so you don't need clutch. So when Formula E started 10 years ago, initially, because we came back from the Formula One background, we started building 2 or 3 gearboxes. Also because the electric motors at the time were a bit limited in the top speeds they could achieve. So having a second gear or third gear was extending that curve a bit. But as we developed the electric motors more, we're able to fulfill the torque requirements, enough torque to nearly spin the wheels at low speeds, and then have a constant power curve up to a maximum speed, which is the maximum speed of the vehicle. So from looking from the left-hand side to the right-hand side, that explains a lot of why the electric powertrain is, in my opinion, a much better engineering solution for what we're trying to achieve here. Obviously, it's not all perfect. At the moment, electric powertrain is still a bit too heavy. I'm not talking about the motors themselves are very light. So in 424, we have 3 motors, and they weigh about 25 kilos each. And they produce about 300 kilowatts each. But obviously, the mass is coming from the battery. So the battery is here, and the battery weighs about 300 kilograms. So if you compare a battery, which is 300 plus 3 motors, so it's 75, plus the transmission. So the total is nearly 500 kilograms of powertrain. And that compares with a traditional engine, which weighs about 120 or 130 kilos. But then the gearbox would be quite a bit heavier than the single speeds. So the powertrain for a traditional Formula One car will be about 300 kilos, 250. So this is where, at the moment, the electric powertrain is a little bit behind from the weight perspective, but it's got benefits when it comes to Obviously, gear shift, you don't need to gear shift. You've got a full power curve. And not only that, but one of the big problems in F1 is braking and downshifting. So when you're braking in F1 or in LMH at Le Mans, it's extremely hard for the driver to have a very smooth entry to the corner, because each time you shift a downshift a gear, the torque at the rear wheels is changing. There is a small torque from the engine, and you get that sort of, this is why sometimes the driver will lose the car, start spinning or stepping the car. So it's just, when you go to the electric car, when all of this is gone, it just makes you think and understand why the electric powertrain is much better. Another big advantage for me is that you got the battery in the middle, and then you've got this amount of power from the battery, which in our case is 800 kilowatts. And you can very easily decide how much goes to the front, how much goes to the rear. You just have electric cables running. So in our case, we've got a third of the power at the front, 2/3 at the rear, but it can vary as well with our software. But if you think of if you try and do the same with a nice engine, internal combustion engine, you would need a transmission, basically like the rally cars. You've got 3 clutches. Well, you've got 3 diffs. You've got a diff at the front, at the rear, and then you've got a connection front to rear with that prop shaft going through the car, and then the engine connecting all of that. So I think what we're seeing is we're going from less mechanical parts to more electrical cables, and that's where the power is transmitted. The power is going through cables, not through shafts, up to motors that are very close to the wheels. It's just a better way to come up with a powertrain, high performance powertrain for these cars. And this is why 424 has got this advantage relative to the Porsche 919, is that power distribution that we can do. We have a bit more weight on the car, but we have a much better power distribution and no gear shifts. Okay. Before I open these documents, I want to go back in the CAD quickly and show you the powertrain. So at the front of the car, you've got 2 cables coming from the battery going into this box, which is the inverter. If I come back to this image here, all electric cars work this way. So you've got a battery, direct current, a plus and a minus, going into the inverter. The inverter transforms the direct current to an AC current, 3-phase. And that is the way you drive. So it's a pulsating current. And that's how you drive an electric motor of high performance motor. So you find the same architecture here, 2 cables going into the inverter, 3 cables going to the motor. This is a typical Formula E motor that we're using, 25 kilograms, 300 kilowatts. And that goes into a single speed gearbox. Remember when I was talking about material and how we look sometimes at doing these gearboxes in carbon or the casing? But for me, aluminum is still the best material for these. And what you find in these gearboxes is it's very simple. You get the input shaft, a small pinion driving a cross shaft, another pinion driving, in this case, we have a drop gear. So it's not a change in ratio, it's just it allows us to have a spacing between the cross shaft and the diff. The reason we have to do this is the diff cannot be bigger in diameter because the chassis packaging constraints. In other words, if you look at the transmission like this, the transmission cannot be lower than this point here, because that's where the chassis ends, and we have space for aerodynamics. So we have a maximum diameter on the diff, and we cannot connect this directly to this shaft, because if we do that, we're going to have interference between the cross shaft and the diff. So we have this what we call a drop gear. So it's basically a shaft that's spacing out two shafts. This is for the front. For the rear, it's quite similar, but the difference is if it loads, we have two motors at the rear, okay, and they act as like just one motor. They basically enter the gearbox through the same shaft. There you go. So it's two motors connected to the same input shaft. They are basically driving the same shaft. They go at the same speeds. There is here, then you've got your cross shaft a little bit higher. Cross shaft is here, and then the diff. You see, we don't need the drop shaft, the drop gear in this case, because the diff diameter is bigger and can connect directly to the cross shaft. So what I call the cross shaft is the second shaft. So I do it again. So you got input shaft, cross shaft, and then diff. And then to finish, we have these carbon drive shafts that are very, very stiff. Traditionally, in F1 or internal combustion engine, we were using steel drive shafts, but with electric motors, we can have oscillation problems because the rotational inertia of the motors is quite high with the gear ratio, and there is very, very little friction. So we started having oscillations. So we needed the carbon shafts to stop the oscillations. Okay. So I wanted to show you that before I open the specification. So this document is very important. It contains all the specification for the different aspect of the powertrain. So you got, let's start with the battery. The battery here, so here you got all the details about the battery that we need to build for the 424 Nürburgring lap. So as I said, it's 280 kilos. It's got a discharge power of 800 kilowatts and a regen of 600 kilowatts. Here you've got a summary of the energy that we're going to use. Effectively the blue curve. So this is the lap of the Nürburgring. The blue curve is the deploy energy, which goes up to 45.6 kilowatt hour. Then in red, you get the regen energy. So we are regening a little bit, 3.6 kilowatt hours. Not a lot because the braking zones are very short. And then what we call the net energy is the sum of the two is 42 kilowatt hours. This is effectively what the minimum capacity for the battery needs to be. On top of that, we're adding what we call some margin. We cannot build a battery that's exactly 42 because a battery needs a little bit of energy at the top and bottom that we don't really use, just so we don't go into the extremes of the battery cell. So we are going to need a 47 kilowatt hour battery. The voltage is dictated by the type of motor we are using, so we cannot go over 950 volts. Okay. Knowing that, I have built a specification for the battery. So this is at cell level. So we ideally, and this is the battery you see here. Ideally, we would have cells that are pouch cells, so they're flat. Thickness is 10 millimeters, and the dimensions are here. The cell mass is 435 grams, and then the capacity of the cell. So all of this has been defined specifically for the Nürburgring. It means that we need the numbers that really matters is what we call the specific power. So how much power the cell can produce per kilo, and the specific energy, how much energy the cell contains per kilo of cell. These are fairly high specification, and I'm still in the process of finding the manufacturer. We are very close to find a cell that can fulfill this requirement. Then you build your module specification. So the module, we've got 10 of them. You see the 10 towers here. Each one is a module. Each module contains 36 cells. So we've got 360 cells in total. We've got a mass for the aluminum frame. We've got some rubber between the cells, a cap. So the total mass for the module is 25 kilos. And then you go to the pack level, so the full battery. As I said, the power is 800 kilowatts. The voltage will vary because the cell voltage from charged to discharged is changing. So we're going to have a maximum voltage of 828 here and a minimum of 540. And the energy is 47.2. Remember, we wanted 47. The total, this is again the specification. We haven't exactly found the cell just yet for that. This is our ideal battery. The total is 280 kilos. So there is a mass for the fluid that will cool the battery, and then the electric wires, and the tray, which is that carbon tray where we mount everything on. So all the battery is mounted on this flat tray. And then we have a cooling model here as well. I will not go into the details, but as you can see, there's been a lot of work done around the battery, what we need, how we're gonna, what we really need to find. And I'm talking today with a handful of companies, one in America, one in Spain, who can potentially deliver, and one in Germany, who can potentially deliver the cell that we need. If we go to the transmission tab here, that's interesting one. This is, so I started building this specification, and then I designed the gearbox that you see here in Onshape. So the way I build this gearbox specification is I know the maximum speed for the car, which I defined to be 360 kph. That gave me a maximum RPM for the final drive. And I know the maximum RPM for the motor, which is 23.5 thousand RPM. So I have a target for the ratio of 8.4, so 8.4 to 1. So knowing that, so this is the front transmission, this is the rear transmission. So both of them have got the same ratio, okay? The rear is 23 kilos, it's heavier because it's got more torque capacity. And each line is a shaft. So you've got the input shaft, cross shaft, the drop, and the diff at the front. And at the rear, you got input, cross shafts, and the diff. Then I started defining the number of teeth, the module based on experience. That gave me some diameters for each pinion and wheels, some gear ratio for each shaft. Obviously, I had to adjust and try different combinations to find the ratio that I wanted. I recalculate the torque. So the torque at the motor is 280 maximum Newton meter. At the rear, you've got two motors, so it's double. And then for each shaft, I recalculate the new torque based on the gear ratio. Then I know the force that pushes on each tooth of the gear. And this way, I'll calculate the diameter of the shaft. So when you know the torque, you know roughly the diameter of each shaft so that they can effectively, they're strong enough. So as you go through the gears, your shaft is going up in diameter. The input shaft is 20 and the diff is 35. At the rear is going to 47 diameter because the torque is very high. Okay? The force of the tooth as well is giving me what we call the face width. So it's how wide each shaft needs to be, each gear. So if you look at the example here, so let's go to the transmission. So the way I design the transmission is I start from a sketch, and that sketch at the rear contains, you can see, input shaft, cross shaft, and the diff. And when I talk about face width, 11, 30, 30, so that's the front. At the rear, 30 and 66. This is this number here, 30. You see the width of the input shaft gear, which is the same for the cross shaft. And then 50. So in the spec it says 66. I've actually reduced since I need to update the spec because I discussed with some people and I found that 50 millimeter is enough for that sort of loading, for that torque. And then the shaft diameter 45 for the cross shafts is a number that's, so it's 37 in the spec, but some constraints are coming as well from the bearings I'm going to use. So there is space for the bearings here. So you can see a shaft is always starting with a bearing space, then a gear or a wheel, then a pinion, and then another bearing. So this is obviously, that's as detailed as that's what I call the concept model. For the diff, it's the same. We have the bearing space, then the diff is inside there. The space here is for the drive shaft to come in, and the same on the other side. This is enough to then take to a transmission manufacturer, and he will refine everything and design your final gearbox to this specification. You need to add then an oil system as well for lubrication. Typically, you're going to have an electric pump pumping from the bottom of the gearbox and circulating the oil and jetting oil back to the gears. That's not, you can't see it on this model. So that's for the transmission or the gearbox. For the drive shafts, I have some calculations here. And basically these calculations, knowing basically the torque, so maximum torque that we want to apply at the front 4,000 Newton meters, at the rear 6,000. This then allows to calculate the diameter of the carbon shaft with a safety factor and the diameter of the steel ends with a safety factor. That allows me to, I've got a mass as well for the rollers, which are these parts here of 1 kilo. And at the end, I can calculate the mass of my drive shafts. At the front, it's 1.8 kilo. At the rear is 2.1 kilo. And I also have a torsional stiffness for them from these calculations. And what I'm adding to this is knowing the stiffness of your drive shaft, knowing the rotational inertia of your motors, then you can calculate a natural frequency. And this is something quite important when it comes to resonance and oscillation. So typically at the front, we're going to have a drive line that is oscillating at 35 Hertz, and at the rear 32. And typically from experience, it needs to be around 35 Hertz. If it's too low, if it's too soft, it will start oscillating badly. And that's it. That's a summary of the motor spec. So again, I said each motor produces 300 kilowatts. That's just the power versus the car speeds on 4x4. So obviously up to a speed of 130 kph, we are torque limited. And after that, we're power limited. So power increases, and then it's constant power, which is the same as this. Okay. And the last document to look at, but we've already looked at it in the past, but I just want to open it again a last time, is the torque maps. And the torque maps is the software and the calculation, the formulas that help us. And these are the formulas that we will use in the real car. It connects the driver inputs. So knowing the throttle and the brakes and the speed of the car, it calculates how much power and torque is demanded by the front motor and how much by the rear motor. We've got also an efficiency for the front and rear powertrain. So the powertrain are creating some heat, and depending on the velocity of the motor, typically these are very efficient powertrains. As you can see, we are up to 95% efficient, which means that only 5% of the power is lost into heat. At lower speed, we are losing more. We are losing like nearly 20%, but only at very low speeds. Okay, so that's the end of this module. But again, let's answer any question you have on the electric powertrain. Franco.
Hi, Nico.
Hi.
I just wanted to ask you about the rear powertrain. Maybe have you thought about driving the wheels independently? Like, I mean, one electric motor per wheel instead of, well, having the motors linked by the gearbox, so you can play with torque vectoring and the slip the differential.
Yes. So thank you. Yeah, I looked into this. In fact, the Neo EP9 had one motor per wheel. So I played with torque vectoring at the time. So torque vectoring left to right. It's interesting because when we did the Neo EP9 for a few weeks, we didn't have torque vectoring just because it was a feature to be added. And when we put torque vectoring, it helped a little bit, but it's not, on this type of cars, it doesn't add a lot of performance. The problem with doing it on 4x4 is the gearbox would become two gearboxes, more or less, because you would need another cross shaft. Basically, you're going to have a wider gearbox and a double set of shafts. So you're going to have maybe 10 or 15 kilos to the car. And then you're becoming limited by the torque, because when you do that, at the moment, if you think about it, you've got two motors, so you're adding the torque of two motors. and then you're sending that torque left or right from the diff. When you do one motor per wheel, the maximum torque that can go to one side is the torque of one motor. So in some situations, when you're exiting a corner, at the moment we're sending more torque than the torque of one motor to one side. Do you see what I mean?
Yes, yes. Yeah,
So
I
you're starting to
understood.
be torque limited more quickly with a one motor per wheel system.
Right.
So
Well, yeah.
so for simplicity and keeping it, what I know is torque vectoring. Again, I get a lot of the time this question asked. It's a very powerful tool for cars like rally cars, because on rally cars you can play a lot with the yaw and send the cars in different, yaw conditions. But on cars like 4x4 at very high speed corners, you don't need a lot of the left to right torque vectoring is not as powerful. And what we do is front to rear torque vectoring. And actually that is quite powerful already. And for
Great,
simplicity
thanks.
and to reduce the mass, yeah, I haven't elected it. But yeah, thank you for the question.
And also, sorry, so
Yep.
the differentials are open, are like normal
No,
between.
so actually they are limited slip differential. So they are clutched differential.
Okay.
We've got ramps for drive and regen, and it's typically what you find in Formula E. So they are passive, but they are limited friction.
Okay. So drivers can't change the slip. So
Yeah.
it's fixed. Okay. Thanks.
Okay. Wojciech?
How is the steel shaft and carbon shaft connected together?
On the drive shaft?
Mhm.
So ask again. So what is the steel?
What is the type of connection between these two materials?
Yeah, that's a good question. This is actually this is the hardest thing to do. To connect when you try to transmit torque. So typically it's a press fit. So the carbon tube is a bit smaller than the steel tube. And then you've got some grooves on the steel. So it's like spline grooves. And it's basically a press fit. So there's a very high pressing. So there's a very strong force connecting the two. It's not glue. It's just press fit.
Is it possible to calculate the torque that is breaking the connection?
I don't. Sorry. I have this horrible cough for the last few weeks, and I think you've noticed, but it's going away. It's very difficult you can't calculate it. I haven't found any way. We tried. So basically, it's basically there's a manufacturer or more than one, two or three who can do that sort of connection, and they know if you ask for a certain torque, they know how to build based on testing.
As for the gearbox, are you planning to use straight teeth or skewed one?
The teeth are straight, all of them. Yeah. This is more efficient than the skewed one. So the reason why in racing we only use straight gears. That's the most efficient, but it's a bit more noisy, but the noise doesn't matter in racing. For road cars, we have angled teeth for noise, but it creates a little bit of heat.
The another advantage of skewed teeth is the area of connection between the teeth, so it runs more smoothly.
Yeah, but it's you don't really. The noise is not a problem. It's very high frequency noise. But what we are doing with straight teeth is we are limiting the heat generated, so we are not losing power through the gearbox as much.
So it is just efficiency purpose.
Yeah.
And another question about the gear. if you can show the front one,
Yeah.
with this one, this spacer gear, how did you
The
call
drop
it?
gear, yeah.
Will it be supported from one side only?
No, it's got two bearings. This is the drop gear here, and here you've got one bearing and another bearing. So the casing will support that bearing inside.
Okay, so it will be the some structure from the.
There will be
from
structure
the
inside, yes.
side. I see.
It's hard to see, but basically you're gonna have structure here going to the top and bottom to support the bearing. There is a bearing here.
I was wondering about this bending of this gear without it. Okay, as for the electric part, do you need any voltage regulator to keep the voltage at 900 something?
No, so basically what we do is the inverter here, the inverter is able to run between 500 and 950 volts. So effectively, so imagine the constant is always the power is constant. Effectively, we start the lap fully charged, so the battery is at 900 volts roughly. And this is the best scenario for that, the power being 800 kilowatts and 900 volts. That means the current would be about 800 volts or 800 amps in total. When we discharge the battery, we're still at 800 kilowatts. So the voltage has dropped to 500 volts. So the current is higher. The current is more like 1300 amps. But the inverter is designed to cope with that.
So the power delivered by battery is more or less independent on its actual charge or other factors.
Yeah. We are, well, that's where we need to, the cells are able to deliver a fairly constant power, but the voltage is dropping when it's discharging and the current is increasing. It's not totally true. I mean, we have maybe a small loss of power towards the end of the lap. These are the things that we're starting to look at in details.
Mm-hmm. And considering that the advantage of regenerative braking is not so much, do you pay with something for this possibility and a bigger mass in the regulator or in the inverter or something like this?
So what you're saying is we're only regenerating about 3.6 kilowatt hour.
Is it
So
worth to have this possibility?
What was your question?
To have the regen, do you need any additional equipment that weights?
No, because and I tell you why we need the regen, by the way. It's not just for the energy. No, the inverter and motors, they are designed to work in both ways. So when you ask negative power, everything, the software reverses everything, and it's just the same. It doesn't add mass to the powertrain. But we do need regen because of the diff. That's a really important point. So you can't see it here, but the diff is a limited slip diff with a clutch, as I said. And the way the clutch works is that it's limiting the slip when you're applying torque to the outer wheel of your diff. Yeah? So when you're accelerating, the diff will close, the diff will tighten because you've got torque. When you're braking, you do need regen, otherwise your diff is fully open. And you see it straight away in our Unity simulation. If you remove regen and you brake, you're starting to lock the inside wheel straight away. Do you see what I mean?
So it provides the load to the diff.
It provides the load to the diff so the diff can lock properly. It's an important point because we had a battery manufacturer asking to reduce the regen. We did, but we started having problem under braking where the diff was not tight enough. It's also a story in Formula E, not so much now because the new battery is better. 2 years ago, for the first 2 laps of the race in Formula E, they couldn't regen because the battery was maximum charge. And when your battery was maximum charge, you couldn't regen because you're already maximum capacity. So for 2 laps, they couldn't regen, and the drivers were complaining a lot of an instability under braking. After 2 laps, the regen is available, and then stability, the diff is working again properly.
So kind of load resistor should be needed here to avoid it.
Can we what? Sorry.
Load resistor, so the regen can load the.
Yeah, but you're talking 300 kilowatts or 400 kilowatts. It's a lot of. You'd need a massive resistor. It's something we tried, to be honest, not on 424. It's unmanageable. It's such a. The amount of heat is huge.
Mhm.
So that would be quite a heavy system. So the easiest thing, the best thing is to make sure we can have the level of regen that we want. So regen really is used for that. And the other thing it's used for is, if you remember on the torque map, we have this, the variable brake balance between braking hard and releasing the brakes. And the reason we can do that is because we have a variable regen front and rear, because the friction brakes are a constant brake balance, but we do need to shift the brake balance rearwards going into the corners, and we do it with regen. So regen is really used for vehicle dynamics. Yeah, a lot.
Okay, thank you.
Okay. Wesley?
Yeah, so you mentioned that there is a consideration of the driveline natural frequency of 35
Yeah.
hertz. Is that a specific requirement for electric cars, or do you have the same requirement for petrol cars? And in what situation does this oscillation becomes a phenomenon that's critical?
Yeah. So the 35 hertz, it's not like a number for every situation that will work. It's for this type of application, from my experience, it works well. The higher, the better. But then it means stiffer and stiffer drive shaft. So when we the first time I did the Neo car, we didn't really anticipate this problem. We had steel drive shafts, and the only worry we had is, oh, there's so much torque under acceleration that we don't want to break the drive shaft. So we made sure we designed the drive shaft that were strong enough, not stiff enough, but they were strong enough in terms of strength for the torque, so for the twist. But they were fairly soft. And we did our testing, and under acceleration, no problem. And then suddenly we broke the drive shaft, and the driver said, I broke the drive shaft when I released the throttle, not when I applied the throttle. And what's happened is you go from, the reason was, in your electric motor, you're basically positive torque, and when you release the throttle, you're basically doing a step. You're removing the torque as a step, and that step is creating suddenly you're letting the motor rotate freely instead of being constrained by the torque. So imagine you've got your rotor pushing in one direction, maximum power, and then you're releasing that very quickly, and it starts oscillating. And that oscillation was enough to go into a natural frequency and create a bigger twist on the drive shaft, and it broke the drive shaft. So where you're seeing oscillations typically on pickup, So each time you've got a fast change of torque. It's not so much the amount of torque, the problem, it's the change. So when the driver picks up the throttle, releases it, goes back on it, you get these oscillations. Another moment where you get high oscillations is if the on a wet track when the grip level is low. So the tires will start slipping and they will grab again, and that will trigger an oscillation on the motor. So the fundamental mechanism is you have an electric motor that's got a certain rotational inertia that's connected very stiffly through a gearbox, and that inertia is multiplied by the gear ratio twice. Because when you look at the inertia at the diff, it's the square of the ratio times the inertia of the motor. So if with your hand you were trying to rotate the diff, you'd find it you'd find quite a lot of inertia. It comes from the motor. And there's very little friction. So it's like a spring without any damping. And the soft part of the chain is the drive shaft. The gearbox itself is very stiff. So now you're left with a fairly big mass, which is the rotational inertia of the motor times the gear ratio twice, that wants to oscillate around the drive shaft. Okay, so consider the two motors plus the gearbox. At this point, it's a fairly high mass, and then consider the drive shaft, because they're fairly long, as like two springs that are soft, and that mass just wants to oscillate. It didn't happen with internal combustion engine, because first of all, you got much more friction for your transmission and for your engine, so that dampens any oscillation you may have. But also the inertia of a crankshaft is very small on the internal combustion engine. So we never had these issues. But on electric cars. So I talked with people who design Tesla road cars, and they have the same problems. So they have had to go to stiffer drive shafts.
That's amazing insights. Thank you. Is there any simulations that can be done to investigate this effect before we make the real car?
Oh, sorry, I'm going around the tabs here. Yes and no. I mean, it's one of these where we found the problem at the track, and then we reversed engineer. We basically created models and saw the same oscillation. And all we did was increase the stiffness of the drive shaft to reduce the amplitude of the oscillation, because what you do is you go to a higher natural frequency. So what happens is the oscillation is still there, but the amplitude is lower because the frequency is higher. And as you know, for an oscillating system, when it oscillates on its own natural frequency, the power remains the same. So if you increase the frequency, you reduce the amplitudes of the oscillation. And it's the amplitude the problem, because the amplitude creates the twist in the drive shaft. So what we found is if we use traditional steel drive shaft, then the natural frequency was like 20 hertz. And at 20 hertz, the oscillation amplitude was too high. But it will depend on again, at 20 hertz, it could maybe work if you had more, if you made your drive shaft even stronger with more metal. But they would become very heavy. So what we found is it's better to go carbon and higher oscillation frequency, and we got out of this problem this way. So it will depend on your application, but the rule of thumb is, yeah, if you have problems, you have to go to stiffer drive shafts for sure.
Maybe if the spike in the torque change is the problem, maybe the software can change remove the spike.
Correct. So actually, that's a good one. So we have what we call software damping as well. So the inverter is a very high frequency control system, and when the torque step we need it because the problem is the driver wants the torque instantly. You don't want to wait. So we still allow for the torque step, but then when we see the oscillation happening, we basically control the torque in reverse. So we are damping that torque at the motor level as well. But that's not always enough. So you need both. You need a stiff mechanical system, and you need a bit of what we call software damping as well.
Understood. Thank you. And on the torque maps, could you explain to us why, when you have regen, why at about 400 RPM, below that, why do you not have peak torque before that, for that 400 RPM? Say on your graph on your top left.
Oh, here.
Yeah, that slope there.
Oh, yeah. We could. This is basically a feature built into the torque map, because if you don't do that when you brake and the car goes to a stop, if you still apply the brakes, it was basically pushing the car backwards.
Oh,
Do you see what I mean?
yeah.
So when the car was stationary, if you were pushing on the brakes, the car was rolling back.
Oh, so is that what the clutch 15%?
No, the clutch, if I show you, so the clutch is on the acceleration side. If I change it to 0%, so I remove the clutch effects, I put 1 because there's a problem. You see all these lines are going very steep
Oh,
because each line is a constant power line. So it's a part throttle, and it calculates the torque for a constant power. But when you do that at very low speed, you get this. So imagine the car is stationary and you put your foot on the throttle. You get extremely sensitive throttle pedal. For just 5% of throttle, you're asking for maximum torque. So the clutch effect is affecting this zone only, and it's creating a degree of control on the throttle pedal. So that you can, and it's just a simple calculation so that when the car is stationary, you get a pedal that's softer when you press, and the car will not jump,
so that's a software clutch, not a physical.
No, it's purely software. It's purely affecting the maps. It's what torque do we demand for the throttle position we're in. But if you notice, it doesn't affect when you're on the track, because on the track we never go below this point.
Yeah.
The car is never slower than that. So it's just to pull away from 0 speeds.
Yeah. Understood.
I call it clutch because it feels like it's what we would do with an old car with a clutch.
Yeah, understood. Thank you. Thank you for your answers. Very clear.
No problem. No, it's very nice for me to explain all these features because, it's things that have developed over the years and features that are really important, but they've been really generalized as well and made them very simple, but they are required for certain what I call edge cases. An edge case is when the car may be stationary. It doesn't matter when we break the record, but it matters because you need the car to be usable in certain conditions. So great, thank you for all your questions. Wojciech, yeah.
One more question about the drive shafts. Do you also check the frequency for the other vibrating modes, like for bending?
Not for bending, no. It's purely for torsion.
Don't you think that if the bending natural frequency is close to the frequency of the transmission, it could
But the tube is, when you look at a tube like this, the bending is very, very stiff.
Mhm.
You're probably, if I think of it, I'd probably think the bending natural frequency might be 200 or 300 hertz, maybe 400 hertz.
Mhm.
So you see, that's interesting, and I'm glad you're asking, because it's all about order of magnitudes. We're talking about 30 hertz for the drive line, big oscillations. The bending is going to be at a much, much higher frequency, and you're not going to even see it. It's going to be very, very fast. So you're never going to be into trouble in terms of breaking anything at that frequency.
What about any backlashes that could effectively reduce the stiffness?
The backlash is backlash is that sort of gap between the teeth.
Mhm.
It's extremely small on this sort of.
I don't mean between the teeth, but between this rollers and the wheels.
On the drive shaft, on the rollers.
Yeah.
It's very, very small, to be honest. You can feel it. I mean, if you take the wheel in your hands, it will take maybe 5 degrees of backlash. But when you drive the car, like, I've never had a driver feeling the backlash, and we cannot see it on the data, because at that speed, the 5 degrees is instant. It's like 1 millisecond or less. Do you see what I mean? The backlash doesn't, and because we're always either on positive torque or negative torque, you're never really oscillating around the backlash, because you're always loading your gear positive or negative. So the backlash doesn't really come into effect. Because backlash is around zero torque, and we are never at zero torque. You see what I mean?
Except for the situation of having the zero throttle suddenly.
Even at zero throttle, we are not at zero torque. If you look at, we've got this thing called.
Oh, okay. I get it.
You know, we've got the overrun torque. So at zero throttle, we're still producing minus 300 Newton meter. We're slowing down the car just to have that handbrake effect for vehicle dynamics. So you'd never feel that. And if you would put zero overrun, then yeah, your transmission might have a bit of backlash, but it won't have any effect, because at that point you're at zero torque. There is no oscillation, no energy, nothing that can actually affect the car in any ways. Do you see what I mean?
It's clear now.
But we have looked at backlash in the past, thinking it could be an issue, but it's not. We don't want a lot of backlash, because it would maybe damage, when you go from negative to positive torque, it could maybe create a little dent on your rollers, but so you don't want a lot of backlash, but the backlash is very small anyway on these cars. Okay, any last question, or is it a wrap? But I really hope you've learned things. I really hope you, I feel privileged of having taken the time with you guys to dig really deep into the engineering of 424. Obviously, we're finishing this series today, but it's the beginning of transmitting as much as we can. It's an open source project. Obviously, when the car starts being built and the project exists, all of that information will become even more valuable, because people will see the value of the car, therefore they will want to access this information. So I'm really happy that I took the time with you to create these videos, answer your questions, and these videos will always stay on YouTube. It will, we'll look back and also use it as the way to explain that we've always had this philosophy of sharing everything about 424, and we've done it this year with you guys. We'll do it again in the future. And as I say, as the car becomes real, it's everything will become more valuable, and I'm hoping that more and more people will get interested in using our knowledge and reusing the learning from 424. So this is the beginning of something. It's not the end. It's the beginning of something. And I'm also thinking in the future. We want video produced in a different way, and there will be more quality associated with it. It was the first time we did this. I really like the fact that we could interact easily with you, and obviously we've done that with the WhatsApp group as well, which will remain live, and we'll use it for other things. So please stay in WhatsApp, stay connected with the team, and as always, if you have any question about things that I've explained, come on WhatsApp, come on pairing.com. I'm hoping that you will also want to take ownership in the tokens, and so think about this as an investment for you and as a way to be more connected with the team as well. So thank you for your time, and I'm sure we'll speak again very soon.
Thank you, Nico. It was really
Thank you
pleasure
very
to
much.
hear all these modules.
Welcome.
Thank you. Thank you.
Thanks, Lauren. Thanks, Wesley. Thanks, everyone, for participating. Bye-bye.
See
Bye,
you
Nico.
soon.
Thank you so much.
Thank you. Bye.